And I call it solution stoichiometry, but it's really just any kind of stoichiometry that involves the molarity equation. So the heart of stoichiometry is all, and this map's kind of going to grow a little bit. The main thing that makes stoichiometry is that you're going with a chemical reaction like we have on the board in green there. You have a balanced chemical reaction, and you go from moles, I'm just going to say moles of A, that's like the given substance that you're starting with, and you're converting it into moles of B. You always do that using the mole ratio, which is kind of the idea of what you do with a BCA table. If you like to do the full-on table, you can do that. Or I've noticed a lot of people really like the ratio method, which I like too a lot. This is just where I'm going from one substance, I'm dividing by its coefficient, multiplying times its coefficient, either with a ratio or just doing it on the chemical reaction like that. This happened to be a 1-to-1 ratio, so it's the same number. If this had been a 3 here, obviously I would have multiplied times 3 and gotten 3 times that amount. That's what makes it stoichiometry. So if you're going from moles of one substance to moles of another substance, you're doing the stoichiometry. But there's lots of ways to get in and out of moles. Last chapter, and chapter 3 stuff, we did a lot of mass to moles conversions for this stuff. So mass was grams, and you remember you used the molar mass. You would divide by the molar mass to do that part. I'm still going to do some more of that. But we're going to add a new way to get into moles today, just like we did at the beginning of class with that bell ringer. You could also start off, and I'm just going to use a big beaker to represent this to remind us that it's a solution here. So if I have a beaker solution, I might know this solution's molarity. If I just had the molarity, would I have been able to calculate moles in the bell ringer? I also needed liters, right? I needed a volume of some type. So I need a molarity and right here, a volume in liters is what you need it in. So you need molarity and volume. And when you do that, you can say, oh, okay, here's that formula we learned. Moles equals molarity times liters. Some questions you might start off with grams, and you might start the stoichiometry. Other questions you might start off with molarity and volume, just depending on what's given. If they give you some grams, you can probably start off with grams. If they give you a molarity and a volume, you can start off with that. All right, and then on the lower side, after you've done the conversion with the balanced chemical equation, you got to get out of moles for a lot of questions. The question might say, well, how many grams of product would you make? Or how many grams of a reactant would you need? Well, that's the same that we've been doing. Use molar mass of compound B for that. And then, of course, you might want to also, the question might have been something like, again, we could have worked this problem backwards. If I said, I made 0.05 grams of copper, what was the molarity of the 10 milliliters of the solution? So I might have worked a problem like this backwards, and my last step would have involved molarity or volume. So again, I'm going to make a beaker down here. It's going to be a short beaker. But the thing is, in this beaker, I'm going to say molarity or volume, because you are probably going to only solve for one of them. Say molarity or volume, depending on which one the question's asking you to find. But once again, I can use the same old equation, this idea that moles equals molarity times liters. I might be solving for molarity or I might be solving for liters. I probably already know moles because I just found moles of B as I worked through the stoichiometry. Right. In a couple more units that we study, a couple more chapters, we'll actually add something else to this mole map, which is gases. But for now, this is the mole map we're going to work with. We just have more options now. You notice on the left-hand side, I'm not doing Avogadro's number or particles because it's not really useful. You're not going to try to find the number of copper atoms in the test tube. That wouldn't really be all that useful to find. You could if you needed to, but who cares how many atoms are in there? It's like billions and billions. All right, so the most important distinction here is the word and versus the word or. You're going to read story problems, and they might only give you a molarity, but they don't give you a volume. If that's the case, there's a good chance that's going to be something you do at the end of the problem, not at the beginning. You're only going to use molarity and volume in this equation if they give you both molarity and volume of a given substance to help you start the story problem. All right, so let's flip the sheet over and kind of like a 3 or 4 step method for working through these stoichiometry problems. Step 1 is done for you a lot of the time, which is you need a balanced chemical equation. Because when you do that, most important, the middle step of stoichiometry, you want to make sure if there is a coefficient here other than a 1, you need to make sure you're multiplying or dividing by the correct number. So you need a balanced chemical reaction if they don't give you one. All right, step 2, I like to list the things I know from the story problem. So with a very simple stoichiometry problem like we might have started with last chapter, maybe there was only one thing given, so you knew what to start with. In some of these questions, it's going to make a lot more sense to kind of make a plan. So if we list what's given and we list what's wanted, that's going to help us make a plan, and we can use that mole map to figure out what our steps are going to be. We can plan ahead that way. All right, let's do a couple of examples, and then time to practice after that. So the first one on here says, how many grams of lead 2 nitrate, now this means I'm going to have to write a chemical reaction for this one, of lead 2 nitrate are needed to fully react 23.5 milliliters of 0.55 molar sodium chloride in the precipitation of lead 2 chloride. So my reactants are lead 2 nitrate and sodium chloride. And then that lead 2 chloride is one of my products. So first let me write myself a nice balanced reaction. I know lead nitrate are going to react with, I think the word with would have made that sound better, sodium chloride. I'm going to leave some space for leave some space to balance this thing. It's lead 2 nitrate, so its charge is 2. Don't want to run out of space here. Sodium chloride is NaCl, of course we know that. All right, then it's the precipitation of lead 2 chloride because lead and chloride are going to get together, and they're even telling me that's going to be the precipitate here. It's Pb with a 2 plus charge, so PbCl2. That's my solid. Plus I got one more reactant here, almost off the screen. Maybe I can squeeze it in. What's the other product going to be here? Good job. NaNO3, you got it. Sodium nitrate. We know that one's aqueous because it's got a group 1 metal and it's got nitrate. All right, just in case, we need to make sure we've got this balanced in case those coefficients are important for this particular problem. They probably are. Balance practicing again. I've got 1 lead on the left, 1 lead on the right. I've got 2 nitrates on the left, but I've got only 1 nitrate on the right. So let's put a 2 there to balance the nitrates. That means I need a 2 over here with the sodium chloride. And now I think I've got a balanced chemical reaction. That was step 1. No stoichiometry yet, but now we're going to get into the stoichiometry stuff. Let's list what's given in this particular question. So they're telling me, as far as numbers go and values go, if I'm looking up here at this reaction again, This is some information that's given. I want to pay close attention to not just the numbers, but also the substance that it's about. All right, it's given I have 23.5 milliliters of, I'll leave a little bit of space underneath the reaction too, because I like to do my stoichiometry right underneath it. So the given information here is 23.5 milliliters of 0.55 molar NaCl. All right, that's the only quantities they give me here. Oh, look, they give me a volume and a molarity. So that really helps me figure out where I'm starting on this mole map thing. It's a volume and a molarity. All right, you figure out what's wanted. What do they want me to find in this question? Hello, this is Richard. Yeah, I'll send her. Sure, fine. Claire, can you go down to the main for just a second? Take a peek all past from here. Right here. All right, what do they want me to find? What's the question asking about? Will Parker? Good. It's not just, yeah, exactly. So you're specific. They want me to find grams or mass of lead-2 nitrate. So now I can go back to my mole map and I know where I'm starting and I know where I'm going, so I can follow a path and I kind of know my plan. I'm starting with a molarity and a volume. I need to change it to liters first, but that's easy, just move the decimal. Then I'll use moles equals molarity times liters. Then I'll use my balanced chemical equation, multiply and divide with coefficients, or if you want to do the times in a line thing that a lot of you like to do, that's great. And then my last step is going to be to make a hard right at the bottom of that mole map and get into grams of the substance. All right, so I'm going to try to squeeze in step 1 at the bottom of the screen here. Step 1, I want to use this. Moles equals molarity times liters. I'm going to move this decimal 3 places to the left there, so it's liters instead of milliliters. 0.023. 5, I think that's what it was. Yeah, liters times 0.55 molar. So I've got 0.01, let's see, with sig figs. I need at least 2 sig figs. I'll carry a third until the end, so I'll call this 0.0129. Moles, and this is where it becomes really important. It's through stoichiometry. Not just moles, but moles of what? What am I dealing with right now in terms of the substance? Sodium chloride, good. I have to write that on the side of the screen. There's so much going on here that if I don't keep up with my substance, I'm going to get lost. Even if I have to write it sideways. All right, so I'm going to take that 0.0129 moles, and I like to put it right underneath here so I can really see what it's about. It's moles of that. All right, again, we made a plan already, so we know where we're going. We're going to lead-2 nitrate. So that means I need to go this way with my stoichiometry. I need to convert moles of NaCl, let me put it down here again, moles of NaCl needs to be converted into moles of PbNO32. So I'll divide by 2 and times 1 if you like to use the chemical equation to do your stoichiometry. And that means I now know my moles of lead nitrate is 0.00646. overemphasizing the substance just to make sure I know what substance I'm dealing with here. Usually I just write the numbers right underneath the chemical reaction right there. All right, so I've gone from molarity in liters to moles of A. I converted from moles of A to moles of B. I'm going to do a different substance now. And I want to get my final answer in grams though. So if it had asked for moles of PbNO32, I would be done. So my last step I'm going to have to put on the board because I'm out of space up there. This one was asking for grams, so my last step is a molar mass step, kind of like it was in the example with the bell ringer there. Moles, and again, I'm going to emphasize moles of lead nitrate, so I don't forget that. Moles goes on the bottom, grams goes on top, and I need to find the molar mass. I know lead's pretty heavy, so it's a pretty big molar mass. So it's 207.2 plus, got 2 nitrogens, so 2 times 14. 14.07. And then how many oxygens are in this compound? Got 6, yeah, so 6 times 16. 331.34. And when I'm doing stoichiometry problems, I like to number my steps. I call this my step 3. So step 1 was getting out of molarity in liters. Step 2 was doing the stoichiometry with the mole ratios up there. And then I call this step 3. So that gives me my final answer here. I would normally write it to the right, but the wire's in the way. So I'm going to get 0.2 or 2.14 grams of lead nitrate. So you have to read your questions closely to keep up with the correct substance. This one was a little extra sneaky. They mentioned lead 2 chloride in the problem, so a lot of times I've worked it through. Yeah.
How do you know how many you want to use of the numbers?
Well, I can have one extra one, so I'm safe, but to be perfect, I should have just gone with that number. And the way I know that is because I go back up to my original story problem. 23.5 had 3 sig figs, right? 0.55, how many sig figs are in 0.55? 2. So my final answer should just have 2 sig figs. I like to keep an egg, so I knew as I started I needed 2 sig figs in my answer. I forgot by the end. So the best way to do it, if you need 2 sig figs in your final answer, work through the problem with what we call a safety digit with a 3rd sig fig. That way I had something to base my rounding on. I had a 4 there. I didn't put it in my final answer on purpose, but it's there. So having that safety digit at the end gives me something to round to in my final answer. As long as you keep 2 throughout the whole thing, you're going to be pretty safe because you're allowed to be off by that 1 extra sig fig. But the best way to do it is to determine your number of sig figs at the very beginning. I need at least 2 sig figs in my answer. So as I work through, I'm going to work with 3 sig figs throughout. If I needed 3 sig figs in my final answer, I'll do my best to work with 4 sig figs throughout the problem. So I have a 4th one to round my final answer to. So I call that a safety digit. If you're using a really good calculator, you can just keep all your digits in it and just go work off that answer, and then you'll have lots of safety digits, so there's nothing wrong with that either. All right, any questions about this first one? All right, we're going to do one more example. I think in this next example, it will be a little bit of a different order as far as following the mole map. This one, along with the bell ringer, we kind of followed the same track on the mole map. If I can get this to go to the next slide. There we go. Okay, so this one says how many milliliters of 0.75 molar sodium hydroxide are needed to neutralize 275 milliliters of 0.50 molar nitric acid. All right, so step 1 is I need to come up with a balanced chemical reaction equation. I see that word neutralize. This means this is acid-base neutralization taking place here, and I see I've got some strong acids and strong bases mentioned in the problem. So I'll start this one off. Maybe just underlining some important stuff. It says sodium hydroxide are going to neutralize nitric acid. Those are my two reactants in this acid-base neutralization. All right, so help me out with the formula here. There we go. What's the formula for sodium hydroxide, Davis?
NaOH.
NaOH. Strong acids and strong bases are always aqueous. It's kind of what makes those bases the strong bases. AC, what's the formula for nitric acid? Have you been studying your strong acids? You know nitric acid? Yeah, it starts with an H. It's hydrogen nitrate. So what's nitrate? Yep. All right, it's also aqueous. Then now we've got to have some products over here. Remember, acid plus base makes salt plus water. In this case, base plus acid makes salt plus water. Mackenzie, what's one of my products going to be here?
H2O.
H2O, good one. You got it. We'll put liquid there. All right, now the salt part here. Pavitra, what's my other product? Oh, the same answer you gave me last time. NaNO3. All right, can we see the blue on there? Yeah, so that's aqueous. All right, this one looks like it's balanced already. I got one sodium on both sides. I have two hydrogens on both sides. Nitrate stuck around, and then the oxygen from hydroxide became part of the water. So it's a 1-to-1 ratio. That's nice. Now, this is where that and versus or becomes really important. To start stoichiometry problem with molarity, I need a molarity and a volume. One of the substances just has a molarity. One of the substances has a molarity and a volume. So I can only start with the substance that has both a molarity and a volume. So I'm going to call that my given substance. All right, my wanted substance, if you look at the bottom of the mole map that we drew a minute ago, if I have a molarity or a volume, that can be a wanted substance. So I need to find out how many milliliters of 0.75 molar NaOH I need. All right, that means we're going to start this one like we did the last one with a molarity times volume formula. Got to have it in liters though, so I'll move that decimal 3 places so it's in liters. .50 molar, which means moles per liter, times 0.275 liters. All right, that's about 0.138 moles. And what substance am I dealing with right now? Adam? Good job. I'm dealing with the nitric acid at this point. All right, so now step 2 is where I go from one substance to another. It's going to be really easy with this problem. Why is it going to be really easy with this particular problem? 1-to-1 ratio, you got it. There's no coefficients here. Divide by 1 times 1. So you don't even have to do that. You know it's a 1-to-1 ratio there. So then I'm in step 3 is what I call it now. I'm at the bottom of the mole map. Last time on my mole map, I took a hard right to grams because the question was about grams and I used molar mass. This time I'm going to kind of go down to that beaker that I drew, and I need to use the molarity equation again. But now I'm dealing with my wanted substance. So I'm dealing with the information about sodium hydroxide there. I still like this arrangement of the equation though. I guess this time though I'll have to solve it underneath it. So I'm going to have to move to the board again. All right, so for my moles, I'm going to use the number 0.138. So molarity is now 0.75 because I'm dealing with the NaOH. And I'm going to solve this for liters. I'll call it L. It's kind of weird to call it L instead of V for volume, but that's how I like to do it. So my number of liters is going to be 0.138 moles over 0.75 molar. This will give me liters, and then I'll change it to milliliters for my final answer. 0.184 liters. All right, how many milliliters is that? 184, you got it. So for my final answer, I'm going to put it back on the main screen. Just if somebody's following along, they can see that. So for in the end, I got this. Which becomes 184 milliliters. And I'll just give a complete answer of 0.75 molar. I think it was 0.75 molar. Yeah, sodium hydroxide. And once again, I get to the very end and I realize, oh, I got my one extra sig fig hanging out there still. So to be perfect with my sig figs, I'll just round this down to 180. All right, so that's solution stoichiometry. In tomorrow's lab, this is the kind of stoichiometry you'll be doing in the lab with a neutralization of an acid and a base. Those are the ones where you got to keep up with the molarity of individual substances, or sometimes the volume of the individual substances. Keep up with your substances really well as you work through these. What questions do you have about those two?